Hello students, welcome back to Learn 24. In this video, we are going to discuss the vapor pressure of liquid solutions. Let me give you a definition to the vapor pressure. Vapor pressure is the pressure exerted by the vapor of liquid in equilibrium with the liquid at a particular temperature. Let me give you an example. I took one glass full of water and I kept aside for a long time. And when I came back, I was wondering what happened. Half of the glass was empty. Can you tell me what happened? Yes, vaporization took place. The water molecules became vapors. That vapors will exert a pressure on the solution, and that pressure is called the vapor pressure. The vaporized molecules will exert a pressure on the solution, and that pressure is known as vapor pressure. Clear with that? Okay. Now, the vapor pressure of liquid solutions. Solvent and solute are liquids, are volatile liquids. They can vaporize. They are called volatile liquids. Now, consider I have a solvent A and solute B. Solvent A and solute B. Now, these are the vapor molecules of component A, and the pressure exerted by these molecules on the component A is known as the vapor pressure of that component. I can represent that as PA0. PA0 is the pressure exerted by these molecules on the surface of this component A. Similarly, the solute B, there are some vapor molecules. These vapor molecules will exert a pressure on B, and that pressure is known as the vapor pressure. I can represent that as PB0. PA0 and PB0 are the vapor pressure of pure substances. Vapor pressure of pure substances. Now, in order to get a solution, I have to add this solute to the solvent. Then I will get a solution called AB. When I add B to A, I will get a solution AB. And the pressure, the total vapor pressure, is contributed by both A and B, called as partial vapor pressure. The total vapor pressure of AB is contributed by both the components A and B, called as the partial vapor pressure. So I can write P total is equal to PA plus PB. PA and PB are the partial vapor pressure of A and B. P total is equal to PA plus PB. That is the partial vapor pressure of A and B. Now, PA is directly proportional to the mole fraction of A. Mole fraction of A. P is directly proportional to mole fraction of A. In order to remove this proportionality sign, I added a constant called PA0. Now, PA will be equal to PA0 into mole fraction of A. Similarly, PB will be directly proportional to the mole fraction of P. In order to replace this proportionality sign, I added a constant called PB0. Now, PB is equal to PB0 into mole fraction of B. This is called the Raoult's law. This is the Raoult's law. Now, as I told you, the total vapor pressure is contributed by both A and B. That is the partial vapor pressure of A plus partial vapor pressure of B. We know the equation for PA and PB. Just substituting that equations in these terms P and PB. That is PA0 into mole fraction of A plus PB0 into mole fraction of B. Hope you remember this equation. Mole fraction of A plus mole fraction of B is equal to 1. Don't forget this point. This is so important. So mole fraction of A plus mole fraction of B is equal to 1. And I can write mole fraction of A is equal to 1 minus mole fraction of B. Mole fraction of A is equal to 1 minus mole fraction of B. So I am just substituting mole fraction of A as 1 minus mole fraction of B. Then I can write PA naught into 1 minus mole fraction of B plus PB naught into mole fraction of B. I am just multiplying this term with the components inside the bracket. So PA naught into 1 is equal to PA naught minus PA naught into mole fraction of B, PA naught into mole fraction of B plus PB naught into mole fraction of B. Here the mole fraction of B is common, right? So I took it outside. I just took it mole fraction of B outside. That is PA naught plus mole fraction of B into remaining terms PB naught minus PA naught. So I got the pressure is equal to PA naught plus mole fraction of B into PB naught minus PA naught. This is the equation for Raoult's law. Don't forget, this is the equation for Raoult's law. Now let's discuss the graph of our Raoult's law. I took vapor pressure on y-axis and mole fraction on x-axis. I can read the mole fraction in both the direction. For example, here mole fraction of A is equal to 1. As gone to the right side, mole fraction of A became 0. And here mole fraction of B was 1. Coming to the left, mole fraction of B became 0. Clear with that? Yes. Here mole fraction of B is 0. So the pressure is only contributed by the component A. That is PA naught. I marked PA naught here. And here mole fraction of A is 0, hence the pressure is only contributed by the component B. So the pressure PB naught I marked here. Now let's read from here. Here the mole fraction of A is equal to 0. Starting from 0, pressure just increasing and I got the line PA, that is the partial vapor pressure of A. I got partial vapor pressure of A. From here, the mole fraction of B is 0. Starting from 0, PB naught. I got the partial vapor pressure of B. I got partial vapor pressure of B. And by joining these 2 points, I got the total vapor pressure. I got the total vapor pressure, that is the partial vapor pressure of A plus partial vapor pressure of B. That is the total vapor pressure. This is the graph of Raoult's law. Hope you got it. And now let's discuss the vapor pressure of solid in liquid. We already discussed liquid in liquid. Now let's discuss solid in liquid. Solid is non-volatile. We are adding a non-volatile solute or the solid and a volatile liquid or the solvent. Now this is the solvent. A is a volatile solvent A. This is the vapor pressure and the pressure exerted by this vapor is called as the vapor pressure. I can represent that as PA naught. I can represent that as PA naught. When I added a non-volatile solid or the solute, this green color as the non-volatile solute, they deposited on the surface of this solution. Now this component A cannot escape so freely because these surfaces are occupied by these non-volatile solids. So the pressure just decreased. In the solution, the total vapor pressure is so less when compared to the pure component. The vapor pressure is lower than the pure component. That is, PA is less than PA naught. PA is less than PA naught. And the pressure, the total pressure is only contributed by the component A since the component, the solute is non-volatile. Is only contributed by component A. So I can write P is equal to PA. P is equal to PA, and PA is directly proportional to the mole fraction of A. PA is directly proportional to mole fraction of A. In order to remove this proportionality sign, I added a constant called PA naught, and the equation became PA is equal to PA naught into mole fraction of A. This is the condition of the vapor pressure of solid and liquid. Now, what is the Raoult's law as the special case of Henry's law? It's an important topic. The Raoult's law as a special case of Henry's law. The equation for Raoult's law, as we know, Pi is equal to Pi naught into mole fraction of I. It's a general equation, that is PA is equal to PA naught into mole fraction of A, and PB is equal to PB naught into mole fraction of B. It's a general form. And Henry's law equation, P is equal to Kh into X, mole fraction of that gas, and the Henry's law constant Kh. These are the two equations for Raoult's law and Henry's law. When these two equations become equal, can you tell me that? Yes, when Pi is equal to Kh, these two equations will be equal. That is, Raoult's law become a special case of Henry's law when Kh is equal to Pi naught. When Kh is equal to Pi naught, Raoult's law become a special case of Henry's law. Now let's discuss about the ideal and non-ideal solutions. First, ideal solutions. Ideal solutions obey Raoult's law. Ideal solutions always obey Raoult's law. And delta H mix will be equal to 0. That means there should not be a heat exchange when the reaction taking place. That is, no exothermic, no endothermic reaction. That is, delta H mix is equal to 0. And delta V mix also should be equal to 0. That means when I add two components, for example A and B, the volume should be equal to A plus B, no extra volume. That is, delta V mix is equal to 0. Well, consider two components A and B. Consider two components A and B. And in A, the intermolecular force of attraction between the molecules is AA. The intermolecular force of attraction between the molecules will be AA. And in B, intermolecular force of attraction will be BB. In order to get a solution, I have to mix these two components, right? So, the new intermolecular force of attraction created, that is called AB. A new form of intermolecular force of attraction is created, AB. In ideal solution, this AB will be almost equal to AA and BB. AB will be almost equal to AA and BB for ideal solutions. If the solutions obey these conditions, the solution will be ideal. This is the conditions of ideal solution. Now, non-ideal solutions. Non-ideal solutions are just opposite to the ideal solutions. Can you guess what? Yes, it will not obey Raoult's law. It does not obey Raoult's law. And also, delta H mix and delta V mix will not be equal to 0. Will not be equal to 0. And the vapor pressure of non-ideal solutions. Vapor pressure of non-ideal solutions will not be equal to the vapor pressure which is predicted by the Raoult's law. The vapor pressure of non-ideal solutions will not be equal to the vapor pressure that is predicted by the Raoult's law. Either it will be higher or lower. Either it will be higher or lower than the vapor pressure that is predicted by the Raoult's law. If the vapor pressure is lower, then it shows negative deviation. If the vapor pressure is higher, then it shows a positive deviation. If the vapor pressure is lower, negative deviation. If the vapor pressure is higher, then it is positive deviation. Let me explain it with a graph. This graph we explained in the Raoult's law, right? These green dots, we already explained about it. This is the vapor pressure which is predicted by the Raoult's law. And if the vapor pressure of non-ideal solution is higher, we can represent it by the upward curve. If it is higher, then it shows a positive deviation. Vapor pressure is higher, it is a positive deviation. If the vapor pressure is lower, downward curve, we can represent by downward curve, that is expected vapor pressure is this green dot and the vapor pressure is lower, it shows a negative deviation. Is the positive deviation and negative deviation. Let me show you some points of this negative and positive deviation. First, AB interactions are stronger than AA and BB. Newly formed AB interaction will be stronger. What happens if it is stronger? It cannot vaporize so easily, right? If it is stronger, we cannot vaporize so easily. Hence, the vapor pressure is lower. Hence, the vapor pressure is lower since the AB is very strong in nature. And delta V mix and delta H mix is lower than 0. Less than 0, it's a negative value. So, the negative deviation. Example, acetone and ethanol is an example for negative deviation. Now, the positive deviation. Newly formed AB interactions are weaker than AA and BB. What happens if it is weaker? Definitely yes, it vaporizes so easily, they can vaporize so easily. Hence, the vapor pressure is higher than the predicted value. The vapor pressure is higher since the AB interactions is so weaker. And delta V mix and delta H mix will be greater than 0. It will be a positive value. So, it shows a positive deviation. Example is the phenol and aniline is an example for that. Now let's discuss the new topic called azeotrophs. Azeotrophs are the binary mixtures having same composition in liquid and vapor phase. They have the same composition. For example, I have to make a solution. For that, I have to mix the component A and component B and I got a solution. But I am mixing these two components in a specific ratio. So when this solution become in vapor phase, the composition of these two components in the vapor phase and in liquid will be same. They are having same composition. Two components will be having same composition in liquid and in vapor phase. Clear with that? Okay. And always remember that azeotropic mixtures are only shown by non-ideal solutions. And these two mixtures or two components that I mixed will be having same boiling point. So they boil at a constant temperature. And also these two components cannot be separated by fractional distillation. They are too close, so we cannot separate them. Alright, now the azeotrophs are of two types, minimum boiling azeotroph and maximum boiling azeotroph. Minimum boiling azeotroph shows a large positive deviation from Raoult's law. What was positive deviation? Yeah, it will have a higher vapor pressure than the predicted value. They will having the higher vapor pressure. Now, what is the boiling point? Can you tell me that? Yeah, it's the temperature in which the vapor pressure will be equal to the surrounding atmospheric pressure. It's called the boiling point. Now, I already having a higher vapor pressure, right? In order to make this vapor pressure equal to the atmospheric pressure, I just require only a small amount of temperature. If I raise temperature in a small amount also, this solution will get boiled because this vapor pressure will easily become equal to the atmospheric vapor pressure, So I require only a small amount of temperature to boil that solution. Minimum boiling azeotroph. Example, ethanol and water mixture is an example for minimum boiling azeotroph. Now, maximum boiling azeotroph show a large negative deviation from Raoult's law. What is negative deviation? It having a lower vapor pressure than the predicted value. Lower vapor pressure. In order to make this vapor pressure equal to the atmospheric pressure, I require a large amount of temperature. in order to raise this vapor pressure to the atmospheric pressure. I require a large amount of temperature to boil this solution. Maximum boiling azeotrope. Example, nitric acid and water. I hope you all are clear with these concepts. Now we studied vapor pressure in liquid solutions. In the next video, we are going to discuss an most important topic called colligative properties. Alright, see you in the next video. Bye bye.